This topic is solutions and types of reactions. And there are different kinds of solutions. The ones we're going to be looking at are aqueous, which remember means that they're dissolved in water. A solute is the substance being dissolved. So if you're making sugar and water, it's the sugar that is the solute. The solvent, because it's aqueous, is the water. And a term that you'll need to know is electrolyte. It's a substance that when dissolved in water produces a solution that can conduct electricity. So things that are ionic can conduct electricity. They are electrolytes. So if I put sugar in water, that's not an electrolyte actually, because it's made of nonmetals. But a metal and a nonmetal, like sodium chloride, would actually be called an electrolyte when it's dissolved in water. Strong electrolytes conduct current efficiently. In other words, we use a conductivity meter and we see that the light bulb goes on strongly. Some things are weak electrolytes. They don't conduct electricity very well, and the light bulb on the conductivity meter would not go on all the way. And some things don't allow electric current to flow. Like I mentioned before, the sugar in water would not allow electricity to flow. So this particular section deals with solutions, just very generally. In the next chapter, chapter 5, we will actually be talking about different units of concentration. But in this particular chapter, we're talking about molarity. Molarity is the moles of solute per volume of solution in liters, so moles per liter. And I know we're all familiar with this from intro chemistry. So for example, a 3 molar hydrochloric acid solution an example would be 6 moles of hydrochloric acid in 2 liters of solution. So here's an example of a question you might encounter. And it says a 500-gram sample of potassium phosphate is dissolved in enough water to make 1.5 liters of solution. What is the molarity of the solution? Well, remember, molarity is the number of moles per liter. So we first have to convert potassium phosphate from 500 grams into moles using the formula mass. And 212.27 happens to be the formula mass of potassium phosphate. So I get 2.355 moles of the potassium phosphate. So that means if I'm plugging into the formula, 2.355 moles divided by the volume. Luckily for us, 1.5 liters is perfectly good because that's the unit we would like for this, and when we do the math, we should get 1.57 molar. Now, something interesting about solutions, we can talk about the concentration of the ions, not just the concentration of the dissolved salt, for example. So for a 0.25 molar calcium chloride solution, you notice how calcium chloride breaks up in this fashion. We have 1 calcium with a +2 charge, but we have 2 chlorines. Now each chlorine is worth -1, so you see that written there like this. So if we're looking at the concentration of the ion specifically, we have 1 calcium, that's 0.25 molar, so the concentration of calcium is 0.25, but chlorine is a little bit different. We can produce twice as many chloride ions as we can calciums, thus there's the 2, and you can see that we have twice as many chloride ions in solution. So let's look at an example here. And this is a perfect example for a multiple choice question on the AP. You will notice you cannot use a calculator on the AP, but there are tricks to apply here. It says, which of the following solutions contains the greatest number of ions? Well, this gets a little bit tricky because, as we notice, we have different kinds of substances. We have sodium chloride, calcium chloride, iron chloride, and sucrose. Now right away I can omit D, because sucrose does not form any ions. so therefore it doesn't break apart. And the others are ionic, and they're going to have a greater potential to break apart. The molarities are all the same, it's only the volumes that are different. So unfortunately, we do have to do a tiny bit of math here. You will notice sodium chloride has 2 ions, the sodium and the chloride. Calcium chloride has 3 ions, and iron chloride has 4 ions. Right, so they're different by number of ions, but they also happen to be different in terms of volume. So now we have to kind of figure out the moles of the compound, and we have to multiply by the number of ions. So for this first one, 400.1 molar. Now I could move the decimal point over here. Milli, is 1/1000th. So this is really 0.4 liters. And then I could multiply by 0.1, and then I would multiply by 2. And I could do the same thing with the other 3 to figure out which has the most. Or, because you notice they're all in milliliters, and because I'm not using a calculator, it might even be easier, because the inaccuracy of the 1000 will cancel. If I multiply 400 by 0.1, I get 40. Times 2 is 80. So I could just kind of do it that way, and I would eventually figure out that calcium chloride, letter B, has the greatest number of ions, because 30, if you will, 300 times 0.1, so 30 times 3 is 90 particles. 200 times 0.1 is 20, 2 times 4 is 80, and we already said the other one is 4 times 2 is 80, so actually B is the correct answer. So even though I didn't put it in the correct unit because they're all milliliters, I could kind of take a shortcut with my problem solving, and the answer is B. Alright, I know we've had this formula before, we'll be using it quite frequently. It's called the dilution formula. So if I have a stock solution and I want to create another solution, I do this all the time when you're working in the lab and you need a different concentration. Before we start the lab, I actually make the solution in a stock room, and then I bring it out to the classroom. Dilution with water does not alter the number of moles of solute present. I'm just adding water, they're just more spread out. You could almost think of the volume or the concentration as different. And the moles of the solute before the dilution equals the moles after, and that's how we come up with this formula, MV equals MV. And 1 means, molarity of the first concentration and its volume equals the molarity times the concentration of the second volume. Because the number of moles remain the same, it works out this way. So, for example, here is a 0.5 molar solution of sodium chloride in an open beaker sits on a lab bench. Which of the following would decrease the concentration of the solution? Well, let's read the choices. If we add water to the solution, or pour some of the solution down the sink drain, or add more sodium chloride to the solution, or let the solution sit out in the open air for a couple of days, or at least 2 of the above would decrease the concentration. So let's go through these. Now, add water to the solution. That's definitely going to decrease the solution, so I like that one right away. Pour some of the solution down the sink drain. Well, that's going to decrease the amount of stuff, but it's not going to change the concentration, so I don't like that one. If I add more sodium chloride to the solution, that's definitely going to change the concentration, but it is not going to decrease it. So, goodbye to that. And then finally, let the solution sit out in the open air for a couple of days. Again, that's going to change the concentration, but as the water evaporates, what will be left behind is the sodium chloride, which will then become more concentrated in that which remains in the bottom of the beaker. So I don't like that either, and obviously if I don't like that, I certainly do not like E. So let's see. Oh, goody, we were right. Adding water to the solution decreases the concentration. Alright, here's a question about dilution. What is the minimum volume of a 2 molar NaOH solution needed to make 150 milliliters of a 0.8 molar NaOH solution? So, obviously somebody wanted to decrease the concentration, and they used a stock solution of 2 molar, and they wanted to figure out how much water they're going to need to do this. This is a straight MV equals MV. M1 V1 equals M2 V2 kind of question. Now, the volume here is in milliliters, and it really doesn't matter if the unit of volume is milliliters or liters or anything else, just as long as the volumes are the same at the beginning and the end. So these two things, let's see if I'm plugging it in correctly, I may not be. What is the minimum volume of a 2 molar? So that's 2 molar would go there of NaOH needed to make. So this volume is actually over here, and obviously the 0.8 would go right there, and we would plug in and we would solve, and hopefully we get 60 milliliters of water would be needed.